Today I'm going to present our work, OmniCache, collaborative caching for near storage accelerator. So this work is done in cooperation with Rutgers, Samsung, and Igalia. So first, cache present across different layers of computer system, including CPU cache, host level page cache, and caches in different hardware devices. So it's important to exploit and combine all caches together in the system to provide the cumulative performance. Therefore, our work proposed to combine host-level I/O cache with near storage cache together. Besides that, the newly introduced technology like Compute Express Link brings a new opportunity to easily interconnect all caches together. So this talk is trying to answer the question about how to build efficient caching design for near storage accelerators. First, let me introduce the background. So this is the latest hardware architecture of the computational storage. First, the modern storage devices are becoming more and more powerful with more than 4 to 16 cores and considerable DRAM size. And second, computational storage can integrate the processor, DRAM, and flash together to eliminate off-chip communication cost, which can provide the high-speed interconnect. Finally, CXL enables the low-latency memory access for retrieving the data from remote memory across the devices. Now let me provide the background on different software designs for near storage devices. So for the near storage device with the host file system design, it supports offloading some specific computational tasks to storage, but the file system remains in the kernel. The device file system designs offload the file system component to storage by utilizing the hardware resources, which supports the direct access and also provides the API to combine I/O and data processing operations. So for example, the read compress here, it will read data, compress it, and write it back. Now let me introduce the motivation. So first, we found existing designs didn't exploit the near storage memory for caching. For the host file system design, as the file system resides in the kernel, it suffers high kernel software overheads and the lack of using the near storage memory. For the device file system design, it provides the direct access, but it didn't provide the caching solution, which can't utilize the host and device DRAM for caching. It could suffer the high communication cost between the host and devices. Second, we found there are high data amplification in host cache design. So according to our analysis, there are substantial unaligned application requests in popular real-world application. For example, there are more than 95% requests are unaligned in DiskKNN or RuxDB. And most importantly, unaligned L requests could cause the data amplification in host file system design. So to make it more clear, here is one example. The application trying to read 1 KB data, and the cache gets missed in the page cache. It needs to load 4 KB data block from storage to the page cache, and return 1 KB data back to the application. So there is a high data amplification between the host and device. So we found that the device cache can help reducing this kind of data amplification. Next, we also found the application stall happen frequently when host-level cache size is full. For example, the foreground application keeps writing the data to the user host-level caching, and when the cache size is full, the background thread will start the eviction to evict the data from host to storage. And meanwhile, another thread is issuing the compress write, which will compress the data and write back to the cache. And it will suffer the write stall for waiting background eviction. Therefore, existing designs didn't exploit the device compute and memory, which could impact the concurrent I/O and data processing. Also, we found that the current designs didn't support the compatibility to dynamically decide where to process the request. So with the host file system design, to execute the KNN application, it could decide to execute it on the host, but it may suffer the high data movement cost between the host and device due to its limited memory capacity, and it didn't use the device memory and compute resources. Or it could offload the KN to the device despite its large input data size, which could significantly impact the performance due to the hardware limited resources. Therefore, we propose OmniCache. Instead of using a traditional vertical caching design, we introduce a horizontal caching that exploits the combined compatibility of the near storage, host compute, and their memory resources to accelerate I/O and data processing. So OmniCache is a horizontal caching design to exploit host and device memory. And second, OmniCache accelerates I/O and data processing with collaborative caching design. Third, OmniCache also supports dynamically offload the request to host or device. Finally, OmniCache exploits CXL for reducing host and device combination cost. So next, let me describe the components in OmniCache. In OmniCache, UserLib is responsible for supporting POSIX API and also provides the predefined I/O and data processing functions. OmniIndex, which provides a unified cache view across host and device. We delegate the index management to the host due to its expensive operations. And OmniIndex also provides a fine-grained concurrency control. Next, OmniDynamic, which can support dynamically offload the request between host and device. Finally, the near storage file system can handle I/O and data processing requests and also manage the file data and metadata. Here is an example for I/O and data processing with OmniCache. So first, UserLib is a user library resides in the host. Application need to use the UserLib to communication with the device. And the device side, it includes a near storage file system, which a device level file system. It can handle the I/O and data processing request. OmniIndex, which resides in the UserLib, which is a per-file range tree, it's used to locate the data position, whether in host, device, or in the storage. And also it provides the ability to coordinate access between different threads. So for example, the thread 1 issues a regular operation, which is P right here. It will need to search the OmniIndex to get the corresponding log. And the blue node here indicates the cache resides in the host. Then it just directly overwrites the data in the host cache. Thread 2 issues the data processing operations. So similarly, it needs to search the OmniIndex first and get the corresponding read-write log, and use OmniDynamic to decide where to process it at, whether in the host or in device. So these two threads can execute concurrently across the device and host. Next, let me introduce how does OmniCache can reduce the read-write amplification. OmniCache reduces amplification by increasing the data access on the nearest cache. So for example, thread 1 issues the P read to read 1 KB data. It gets cache miss on the host and then directly loads the 4 KB data block to the device cache first, instead of moving it to the host level cache, and return 1 KB data back to the application from device cache directly. So therefore, there is only 1 KB data movement across the devices. And within the device, it also provides low access latency. Therefore, near storage cache overcomes the alignment-related amplification issue. After that, OmniCache minimizes application stores by collaboratively using host cache and device cache. So for the same example here, the application keeps writing the data to the host cache, and the background thread will start the eviction when host level cache is full. So meanwhile, another thread is issuing the data processing request, which is checksum right here. So in OmniCache, it will get offload and write data to the device cache concurrently without application stores. So therefore, the horizontal caching design for OmniCache can reduce the frequent application store. Next, OmniCache also provides the compatibility to collaboratively using host cache and device cache for processing. So take Kannan as an example. Read distance nearest k is an operation in the Kannan application. It will read a bunch of data block, calculate the distance, and pick the nearest k. So in this example, Omni-index locates the data position, and the Omni-dynamic decides to execute these operations at host side. And meanwhile, another thread issuing read distance nearest k again, but the Omni-dynamic decides to execute at device side. So two threads are executing concurrently across host and device. At the end, they need to merge the result together to do the final prediction. Now the question here is how to dynamically determine where to process the request. Therefore, we propose a model-driven dynamic offloading solution. So first, we found the processing speed depends on several factors, such as data ratio, processor cache, and I/O queuing delay. So OmniCache continuously monitoring the host and device resources before offloading it. And our model will estimate the processing time across the host device to identify the request location. The model is based on three parts, which is data transfer cost, queuing delay, and execution time. Please see paper for more details regarding the model-driven offloading. So at the end, we also explore the CXL extensibility for OmniCache. CXL can enable the host computer to directly access the device memory, so we map the device memory to the host as an additional Nguyen node by using the CXL.memory, and the application can directly access the device memory by using CPU load or store instruction. And the latency is around 200 nanoseconds. So with CXL, we found the OmniCache can significantly reduce the queuing delay and the CPU overhead for pulling the completion queue, thereby minimize the CPU overhead for host and device side. Now let's go to the evaluation section. Here's the experimental setup. For hardware, we're using dual socket, 64-core Xeon CPU, and 512 GB Optane NVM. We emulate our installed file system due to the programmable storage hardware, and we dedicate the device thread for handling L request. We also add the PCIe latency for all L operations. We compare with the following state-of-the-art design: Nova, which is a kernel-level file system, FusionFS, and we build a user-level host cache atop of the FusionFS to represent the device-level file system. We also emulated the Lambda I/O with the OS caching, which represents the near storage design. So our first evaluation goal is to understand the effectiveness of OmniCache for reducing I/O overheads. The macro benchmark, each thread will issue 1 KB I/O request, resulting in a total workload size for 64 GB. Host cache and Lambda I/O employ 20 GB host DRAM cache, and OmniCache uses 16 GB host cache and 4 GB device cache. So total cache size is the same. For random read, we can see that Nova suffers high system call and data copy overhead. FusionFS provides direct access, but it lacks of a caching solution. Host cache and Lambda I/O have better performance, but it suffers high data application overheads. At the end, OmniCache significantly improves the performance by reducing the data movement cost. Similarly, for random write, OmniCache also shows substantial performance gain by reducing the eviction stalls and data movement overhead. Next, we study and validate the benefits of Omni-dynamic. So to validate Omni-dynamic, we conduct an experiment that each thread will randomly read 4 KB data block, calculate the checksum, and write the data back. So Omni-dynamic are using 16 GB host cache and 4 GB device cache. So with read, checksum, write workloads, as we can see, Omni-dynamic improve performance by considering hardware and software factors such as queuing delay, host and device cache load, and near data access. Next, we also try to understand the performance of using the CXL.memory. To understand the performance with CXL, we emulate the device memory as a remote NUMA socket to the host CPU, but local to the device CPU. So according to our result, OmniCache improves the performance by avoiding the I/O queuing delay and CPU pulling over cost with CXL. Finally, we evaluate OmniCache on the real-world application. We first evaluate OmniCache with YSIB on the level DB. As we can see here, OmniCache improves the performance by reducing the write store overheads. And we also evaluate OmniCache on Kannan. As we can see here, OmniCache also provides a better performance by concurrently executed operations on hosts and devices. Therefore, as a result, OmniCache also shows high throughput gain on real-world application. So to conclude, it's important to use all compute and memory sources in the system. We propose OmniCache, which is a horizontal caching design and a scalable caching. OmniCache can effectively reduce the data amplification by collaboratively using host and device cache. OmniCache accelerates I/O and data processing by concurrently using the host and device CPU. Finally, CXL provides the substantial benefits with unified caching design. And our code is already open sourced. Please feel free to try. Okay. Thanks everyone. I'm ready to take any questions.